We now want to look at the halogenation of alkynes. And so just like with the halogenation of alkenes, we can add a halogen like Cl2 or Br2 across the carbon-carbon triple bond instead of the double bond, but we can do it twice. Now, it is possible to add 1 mole, and when you do, you will get a trans-dihalide. And then on addition of the second mole of the halogen, you will end up getting the tetrahalide. As far as the mechanism goes, the first step is just like the step that you see in the halogenation of alkenes. The nucleophile, which is our pi bond, reacts with the electrophile, which is the partial positive charge on one of the halogens. And then one pair of electrons forms, and we get a 3-membered ring that we call the bridged halonium ion. In this case, that bridged halonium ion is the chloronium ion, but it works with bromine as well, as we saw in the previous chapter. In the second step, the nucleophile, the halide, will come in and react with the backside on the carbon. And when we do that, we will end up getting a trans-dihalide. Now, it is possible to isolate this trans-dihalide, but if you have excess chlorine available, then that chlorine will again react with that alkene, and we'll get another bridged halonium ion. And at that point, then the halide will come in and react with that one, and we will get a tetrahalide. So essentially, both carbons that are on the carbon-carbon triple bond will get 2 halogen atoms. So we want to look at problem number 11. All right. So on problem number 11, we've got let's see, 1, 2, 3, 4, 5, 6. So this is the 3-hexyne or hex 3-ine, and we're going to treat it with Br2 and Cl2, and we just want to write down what the products are. And for the Br2, we're adding 2 equivalents. So 1, 2, 3, 4, 5, 6. And so we'll get 2 bromines on carbons 3 and 4. So 2 bromines there and 2 bromines on carbon 4. And so that's for A. For part B, where we've got the chlorine and we're adding 1 equivalent, we're going to get the trans-dihalide. So 1, 2, 3, 4, 5, 6. And so it will be an alkene. And we'll have chlorine there and chlorine there. So we get the E isomer. Technically, we wouldn't call it trans. We'd call it the E isomer because the higher priorities are further apart. But that is what we would get for part, and that is part B. There is no part C. That's for part B on this problem. Okay, so let's go back and let's look at the next reaction, which is the hydration of alkynes. And so the hydration of alkynes is again, similar to the hydration of alkenes, except something interesting happens. So in the presence of a strong acid, and sometimes we'll need to use the mercury 2 catalyst, and I'll talk about that in a minute. We can add H2O across a carbon-carbon triple bond. And when we add it across the carbon-carbon triple bond, we will get a compound that is called an enol. Now, enols are not particularly stable. They will go on. They will form what's called a tautomer, and we'll talk about tautomers here in a moment. It will rearrange and form what is called a ketone. So, and so if you do it on an internal alkyne, you can use just water and sulfuric acid. If you are doing a terminal alkyne, you will get Markovnikov addition, and you usually require a catalyst, which is the mercury 2 sulfate, added in with the sulfuric acid and water. and that will help to promote the reaction, and we will get, again, Markovnikov addition, and then we will end up getting a methyl ketone. So let's talk about this keto-enol rearrangement. We call this tautomerization. Tautomers are constitutional isomers that readily interconvert by exchanging the location of a hydrogen and a double bond. And enols and ketones will tautomerize. All right, we're getting all the forms here. We got the noun, and now we have the verb form there. It will tautomerize in the presence of either acid or base. The mechanism for tautomerization is really easy, and we will look at that here in just a moment. So the enol tautomer has an OH attached to a carbon-carbon pi bond or double bond, and then the keto form is a ketone. So the carbons that made up the carbon-carbon double bond include the carbon in the ketone and the adjacent carbon. All right, and that oxygen is the same as that oxygen. So really, all that changes is that this hydrogen ends up on this carbon. So this carbon will go from being sp2 hybridized to being sp3 hybridized. All right. Equilibrium for this will usually favor the keto form, and that is simply because of the difference in energy. It turns out that the pi bond in this carbonyl is much stronger than the carbon-carbon pi bond. And because it's much stronger, this is the favored product. Now, there are some unusual examples where the enol form is the favored product, but usually there's something else going on in that, and we will see that in a chapter next semester. As far as the tautomerization mechanism, it's pretty easy. It's protonate, draw the resonance structure, deprotonate. So protonation of the double bond, when you protonate that double bond, you're going to get this carbocation. We can draw a resonance structure for that carbocation where we donate the pair of electrons from the oxygen to form the double bond, and then we deprotonate, and that's it. So protonate, draw the resonance structure, deprotonate. And that is all there is to it when we are doing the tautomerization mechanism. Now, one thing that I want to point out, this is an acid catalyzed reaction. If you look, we have H3O plus. Usually it's just water with some acid like sulfuric acid, small amount of it. And when you have sulfuric acid and water, you essentially get H3O plus. That H3O plus is used up here, but then when we deprotonate with water later, we regenerate the hydronium ion. So it is catalytic. That means that we don't need one equivalent of the acid to tautomerize. We can do it with a much smaller percentage. All right. So as far as the entire hydration mechanism, we'll go through the steps of it. We protonate the alkyne, and that's going to form a vinyl carbocation. That vinyl carbocation will react with the water nucleophile in a second step, and then we will have a mixture of isomers if isomers are possible here, and then water comes along, deprotonates, and we have the enol. That enol will go through the exact process that we had on the previous page, which is protonate, draw the resonance structure, deprotonate. So if you can get through this part of the mechanism, this part is not too bad. Now, on number 31, we are not going to be looking at the mechanism. We are just drawing the keto form. And this is a very easy problem. So very, very easy. You just find the enol, wherever the enol is, and it's very easy because it's where there's an OH near a double bond. That's our enol. And wherever that oxygen is, that's going to become a ketone, and wherever the double bond is, that'll become a single bond. So our ketone form of this one. All right, so 1, 2, 3, 4, 5, 6. We got that. And our ketone form is this. And that's how easy that is. And if you want, you can draw the arrows to indicate that this is an equilibrium process, and we will have significantly more of the ketone form than we do of the enol form. On this one, because the oxygen is on a terminal carbon, we're not going to form a ketone. We're going to form an aldehyde. So we'll make a double bond there. I'll draw the arrows. So we'll have our double bond to oxygen, and then hydrogen there. So that hydrogen is there to begin with, but it is implied in this structure, and I drew it specifically in this structure. Personally, I think it's weird when you draw aldehydes and have an implied hydrogen. It looks strange. And that is not a typical form. So usually on aldehydes, you will draw the hydrogen if that's what you have. All right, again, on this one, we're just going to put a carbonyl here, and we'll get rid of that double bond. All right, and that is our ketone form of that particular compound. So that is pretty easy, not too challenging. All right, our next reaction that we want to look at is hydroboration-oxidation. Again, we saw hydroboration-oxidation during the previous chapter on alkenes. And something interesting happens here when we do it on alkynes. It's a two-step reaction sequence, and it converts the alkyne to a carbonyl compound. The first step is very much like the first step in the formation of an alkyl borane, or an organoborane, if you want to call it that. So where we add BH3. And again, remember, BH3 is kind of an interesting compound. There's some other stuff that can happen to it. Like you can add it more than once, and sometimes you use other compounds. But BH3, we form the organoborane, or the alkyl borane, in this case a vinyl borane. And then in another step, we oxidize that carbon-oxygen bond. And in doing that, we form an enol. And when we form that enol, it tautomerizes to form this ketone form. All right, so we get that carbonyl compound. And again, that carbonyl bond is stronger than the carbon-carbon double bond, and so that is why we form the carbonyl compound. Now, there's a difference in what happens with an internal alkyne versus a terminal alkyne. With an internal alkyne, it's not particularly interesting. We do get the hydroboration, oxidation of the internal alkyne, and we end up getting a ketone. So here with the internal alkyne, we end up getting a ketone. And that's just like what happens with the acid catalyzed hydration. So if you did this with water and sulfuric acid, you would get this. And if you did this with borane and then did the oxidation, you would also get this. Where it becomes different is with terminal alkynes. With a terminal alkyne, if we use the borane or borane substitute like 9-BBN, we will get addition to this. And then when we oxidize, we will with the hydroperoxide and hydroxide, we will get the enol, but because in that particular reaction it does anti-Markovnikov addition, the OH ends up on the terminal carbon, and when it tautomerizes, we end up getting an aldehyde. So again, same anti-Markovnikov addition that we saw with alkenes, but this ends up giving us an aldehyde versus a ketone, and that is kind of a cool difference. So we want to look at these and on number 16, there are two problems. So I'll switch over my document camera here. And we're going to draw the products formed when the alkynes are treated with each set of reagents. So one with H2O and H2SO4, so traditional hydration, which will do Markovnikov addition. And then one with the borane followed by the oxidation, and that will give us anti-Markovnikov addition. All right. So for this one, I'm going to just circle them as 1 and 2. So reaction conditions 1, we're going to get Markovnikov addition. So hydrogen will go here, OH will go on this carbon, and that's going to form a methyl ketone. So we just need to draw the rest of this. I'll go ahead and draw it just like it is. So CH3, 2, CH2, carbon, CH3. Now, if I were going to draw this compound like normal, I'd do 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. 2, 3, 4, 5. And I would put a ketone right there, and then the methyl there. Those are the same compound. I like drawing it this way. I think it looks prettier. All right. As far as the other product, when we do hydroboration followed by oxidation, so 1, 2, 3, 4, 5. All right, so we still have that methyl there, but since we do anti-Markovnikov addition, this will be an aldehyde on the end. So we'll go ahead and put the H there to clarify. So, and that will be the product that we get. So carbon 1 and 2 are carbon 1 and 2. And then on this one, that's carbon 1 and 2. All right, we're going to do the same thing with this pair of, or this compound, do the same pair of reactions. So our cyclohexane ring stays completely the same. And we'll do Markovnikov addition, so hydrogen will go out there. We'll end up with the carbonyl here. And then reaction conditions 2. We get the anti-Markovnikov addition, so we end up with an aldehyde, so the carbonyl will be on this carbon. We'll put it like that. Oh, it fell off the screen. Sorry about that, but there we go. We'll get the anti-Markovnikov addition. Okay, so let's switch back over. So we now want to look at a reaction that is not an addition reaction. This is a reaction with acetylide anions. We saw earlier that that alkynes have a pKa of about 25, which means if you use a very strong base like amide or hydride, then you can deprotonate them and form a nucleophile. And then that nucleophile can react with any number of electrophiles. A very convenient reaction. So a typical reaction that we really like to do is to do an SN2 reaction where we use this as a nucleophile, and that allows us to make new carbon-carbon bonds. So here we can take this nucleophile, react it with this alkyl halide, doing an SN2, and we end up getting this internal alkyne because we've got carbons on both sides. And we can also do this with acetylide, just straight up acetylide, which is just H, C, triple bond C, and we could end up with a terminal alkyne on that. But it's a great way to add a set number of carbons to the end of a chain. And so very, very useful synthetic step. Now, just a word or two about SN2. As you remember, SN2 tends to work best with less substituted alkyl halides. And so it tends to work best with either methyl, the methyl alkyl halide, like methyl bromide or something, or a primary alkyl halide. So here we've got a primary alkyl halide. This one is chloroethane, and we can make a 4-carbon chain. So here we've got a 2-carbon chain, a 2-carbon chain, and the product has a 4-carbon chain. All right. And here we've got, 7 carbons in this. We've got another 7 carbons here, and we can combine them together to make a compound that has 14 carbons. So it's possible to make small compounds or large compounds doing this process. The caveat here is if you attempt to do this with a secondary or tertiary alkyl halide, you're probably going to get E2 because of steric hindrance. And so instead of the nucleophile coming in, it's more coming in and doing a substitution reaction. You're much more likely to have the nucleophile come in, deprotonate, and form the alkene. And typically, if you go through all the trouble of deprotonating this, you don't want to do this. So you don't want to do the acetylide SN2 with a secondary. You couldn't do it with a tertiary to begin with because, tertiary just doesn't do SN2. But secondary, sometimes we can do SN2, but if you attempt it with a acetylide, it's just too strong of a base. And there's a little too much steric hindrance there for us to do that. The whole point of this is that we get new carbon-carbon bonds. And anytime you can make a new carbon-carbon bond, you are likely to have made somebody's day. Let me emphasize why this is so important. Many, many times, if you go back in the history of chemistry over the last 100 years or so, anytime somebody comes up with a new way to make carbon-carbon bonds, a synthetic reaction that nobody's used before, they almost always end up getting the Nobel Prize for that. Now, there are exceptions to that, and definitely not a universal rule, but it is a big deal to be able to make new carbon-carbon bonds. All right, so we're going to look at number 17 on our in-class assignment. And you'll see that our first step here, we've got this acetylene, and the first step is that we're going to deprotonate that, and we will form acetylide. So we will form HC triple bond C negative, and then that will react with our alkyl halide, and we will end up getting this compound. So I'm going to just write it out like this. So CH3 2 CH2 carbon triple bond carbon hydrogen, and that will be our product. I could attempt to draw this as a line structure. Let's see. So 1, 2, 3, triple bond. All right. So there we go. We got a triple bond, and then that's there. Yeah, it's a little challenging to draw that as a line structure. You can put the hydrogen on the end. That's why I went ahead and did with the condensed type structure. All right, so now we've got another one. We deprotonate, so we would get the conjugate base of this, so the acetylide form of that. And then here we've got a primary alkyl halide, so we could simply add that to the end of our chain. So let's draw the cyclopentane, and then got the carbon-carbon triple bond, and then that's connected to a carbon and an ethyl. So just to clarify what carbons are which, so this carbon is here. The end carbon, the terminal carbon, becomes this one. The carbon that's next to the halogen becomes this one, and then the CH3 is the one on the end. So there's 1, 2, 3, 4 carbons that are now attached to that cyclopentane. All right. Alternatively, you could just draw this with the letters in there and do a condensed type structure. If we attempt to do it with this, this is a tertiary alkyl halide, as we saw on that previous page, this page, right? Tertiary alkyl halides will end up doing an elimination reaction, and so we will regenerate our acid, right? So we deprotonate this with a strong base, and then we deprotonate this with our other strong base that we had made, and so we will have this compound back. And then the other compound that we would get, so this is tert-butyl chloride, we would end up getting isobutylene, which is this. And then chloride, it would be lost, and we have sodium in there. But these are the organic products. So we would end up with isobutylene. So, all right. Let's go back over here. So here is an example of doing a synthesis with acetylide anions, and so here we've got this alkyl halide, primary alkyl halide, the iodide here. The nucleophile, which is acetylide, would come in and react with that, and we would end up with this. There's our new carbon-carbon bond that is shown in red. And then I always like this, like, oh, we got this, and then several steps, and we got this. I have no idea what those several steps are. I have not looked up the paper on this. I expect that it was probably a non-trivial thing to do this. But in case you're curious, these 5 carbons are these 5 carbons, and then we've got 1, 2, and 3. Those become these 3. I'm not sure how the methyls get on there. This methyl is this methyl right there. And then 1, 2, 3, 4. 1, 2, 3, 4. So interesting. Again, I'm not sure exactly what the 2 steps are. Here is another one. You deprotonate it, and then add it to this alkyl halide, and you get this. And then several steps. Again, a lot of somebody's time went into that, and you end up getting this big compound here. So those are just a few examples of synthesis reactions that you can do with alkynes. All right. We now want to look at epoxide ring opening with acetylide anions. So acetylide anions will open with epoxides by an SN2 mechanism. This is a strong nucleophile mechanism, and in this case, since it's a strong nucleophile, the epoxides are going to open at the less substituted carbon. So here our acetylide would come in and react with the less substituted carbon, and that's different than if we had an acid-based epoxide ring opening with a weak nucleophile. Then it usually goes to the more substituted carbon. Here it goes to the less substituted carbon, as your typical SN2 mechanism does. All right, you open that up, and then water in a second step, and that water forms an alcohol. So you open up that ring, and you end up getting an alcohol. Here is another one. With this particular one, the nucleophile comes in. We have a meso compound here that we started with, and so we still have stereogenic centers in the products. And because we start with something that is achiral, that means that we either get an achiral product or we get a racemic mixture. And in this case, it's a racemic mixture. All right, so we now want to look at the product here for number 21. So let's go back over. So we want to draw the products of each of these reactions. So here we've got an epoxide in a ring, and you'll notice that we've got 2 different kinds of carbons. It's an asymmetric epoxide, and with the strong nucleophile, it's going to go to the less substituted carbon, and so it will come over here. It will be opposite the OH. It'll be anti to the OH. All right, so the CH3 would still be there. We would have an OH So it would be alkoxide, but then with water, it would protonate to give the OH. And then our carbon, triple bond carbon, hydrogen, and that would be our product there. All right. With this one, we've got a meso compound, and each of those carbons is equally likely. There's not one that is more likely to be attacked than the other. So we would end up getting two products, and those two products would be enantiomers. So we'd have OH, and then C, triple bond C, hydrogen. That would be one of our products. And then our other product OH, and then carbon, triple bond carbon, hydrogen. All right, and that is our reaction there. So finally, we want to look at a process that we call retrosynthesis. We talked a little bit about retrosynthesis in our last chapter with alkenes, but now we want to look at it with alkynes. And so when we do a retrosynthetic analysis, we want to look at it both forwards and backwards. So I'm going to show you something, a new kind of arrow that I haven't shown you before. This is an open arrow, and we use open arrows specifically for retrosynthesis. It means something different than we use like normal arrows for. In a normal reaction arrow, it says reactants are on the left and products are on the right, and sometimes we'll put reagents right on top of the arrows. But with this kind of thing, this is a sort of brainstorming process. So you'd say, all right, here's our target compound, and we have an open arrow to indicate what a possible precursor would be, and then another open arrow to indicate any precursor to that, and then another however many steps it takes to get you back to your starting material. And so this is truly what we mean when we're talking about retrosynthesis. It's like looking at everything backwards. When we do retrosynthesis, we typically don't put reagents on the arrows. We just put what we think it could be. And there's an advantage to that. One, sometimes when you're thinking of a reagent, you may get some reagents confused. But if you know that it's possible to turn an alcohol into an alkyl halide, then you can put that as a step. All right. But again, the key thing here is that our target, our product, overall product, is on the left, and the things that come before it are on the right. So that is how we think about retrosynthesis. So let's look at an example of a retrosynthetic. Here, this is important. When we're doing a synthesis, we typically have two different kinds of reactions, and we divide our reactions into these categories. One of those categories is those reactions that form new carbon-carbon bonds. Again, this is such an important thing when it comes to organic synthesis. If you have a big toolbox of ways to make carbon-carbon bonds, you are going to be much better at synthesis than somebody who is not familiar with those reactions. And then the other reactions are ones that convert one functional group into another functional group. And we've seen a whole bunch of those, converting an alcohol into an alkyl halide, or converting an alcohol into an ether, or any number of things, converting an alcohol into a tosylate, converting an alkyl halide into an alkene. So we've seen all kinds of these reactions, and we've seen a few of the carbon-carbon bond reactions, and so we want to get even more familiar with those. And we will see more of these reactions as we go further along. All right, so we've got some small type here, but there are steps when we're doing retrosynthesis. We want to compare this carbon skeletons of what we're starting with, like what our possible starting materials are, and what our proposed product is. And sometimes it's helpful to like count up the carbons and make sure that they all match up, um, and you know, keep track of where the carbons are. I've done attempted retrosynthesis where I miscounted something, so you want to be careful about it and count everything properly. Step 2, concentrate on functional groups in the starting material and in the product, and ask yourself the question, what methods introduce these functional groups in the product, and what kind of reactions can I do to the starting material, right? So when you go back and look at all the reactions that we've done up to this point in this class, you look at, well, how are all the ways that I can make this functional group an alcohol? And you may have started with an alkyl halide, and so your question may be, well, what are all the ways I know to turn an alkyl halide into an alcohol? And then sometimes we have to, you know, work backwards a few steps from our product and work forward a few steps from our reactant, and then eventually we may be able to get to our product, or get to a synthesis that works. So work backwards from the product, work forwards from the starting material, and hopefully you can come to a common intermediate. So what intermediate precursor of the product, or what's the immediate precursor of the product? We saw this in the last chapter, and we're going to see another one here, and we'll do an example in just a few minutes. Compare the precursors to the starting material and determine, is there 1 step, 2 steps, 3 steps I can use to get to that intermediate? And always generate simpler precursors when working backwards. So you don't want to get more, when you're working backwards, you don't want to have more complicated molecules going backwards. That's usually not a favorable thing. You want to use as few steps as possible. Sometimes, however, you may have, let's say you have 2 synthesis, proposed synthesis, you know, pathways. You may have one that has 3 steps, but those may be very high yielding steps, and so they may be more favorable than like a 2-step synthesis that doesn't have as good of a yield. So you have to keep that kind of stuff in mind. Now, with what you guys are doing, yield is not our number one concern because we haven't really talked about the yield of reactions. Every single one of these reactions that I've shown you, they are not 100% yield. Some of them are, you know, can be in the high 90s, but none of them are 100% yield. So we'll talk about yield later. All right, and then you may need to work through more than one possibility for a given compound. So you may have an idea and then it doesn't work, and you may have to try something else. And often there's more than one possible way to do it. So, all right, so once you have got a retrosynthesis where you've got the open arrows, then write it out as a normal synthesis process. So write it out as a normal synthesis process. All right, so here is an example of a retrosynthesis. Devise a synthesis for 2-butanone from the starting materials with 2 or fewer compounds. So that means you can start with 2 carbon compounds, and we want to make something that has 4 carbons in it. So here is our target. We have the open arrow, and we want to know what would be an immediate precursor to this. Well, we just saw a way to make ketones. All right, so we saw a way to make ketones, and so that way of making ketones was from an alkyne. So thinking backwards, we could do an alkyne and do regular hydration. So we do regular hydration to get this. And again, we're not putting the reagents on there yet. So do regular hydration of this to get that. Well, now, how could we make this? Well, we know that we can make this bond by doing an SN2 with an acetylide and an alkyl halide. And so here we could use this acetylide and that alkyl halide, and then our starting material would be acetylene. All right, so now we want to write out the reaction in the normal direction. So we're going to take this, and we're now going to write it out in the normal direction. So the first step is we'll take this and deprotonate with a strong base like sodium hydride, and now we have acetylide. With acetylide, we can then treat that in a second step with this ethyl or chloroethane, and we can do an SN2, and that will give us this. And then we can take that alkyne and do hydration. Because it's terminal, we need to use the mercury sulfate, mercury sulfate, and we can get our target compound. So we can think of these reactions sort of in that reverse order. All right. One quick thing that I wanted to mention before we went to our in-class assignment, and that is that when you're doing a synthesis like this, often you'll start off with a mostly pure compound, something you purchased from some place, and then you'll do this where you deprotonate, and then you'll form this, and then that you'll use right away because it's hard to characterize this when it's deprotonated. But then you can react that with some other compound that you purchased, and you would get this. And this is a synthetic intermediate. And because it's a synthetic intermediate, it's something that we isolate and purify and characterize and make sure that it is what we say it is. And then we would do the final step. So if you were just to take like what's left over after you do this and all the chemicals that are left in there and then attempt to do this, it may not work properly. So sometimes you have to switch conditions. So often it requires that you purify your synthetic intermediate. Now, I just mentioned that. That's not something you're going to have to do right away unless you decide to become a chemistry major. All right. Or if you like go to grad school or something in chemistry. So let's head on over to our in-class assignment. We're going to devise a synthesis for CH3, CH2, CH2, CHO. So that's an aldehyde. It's a 4-carbon chain. So I'm going to redraw it as a skeletal type. So there's that. All right. We're going to think of this retrosynthetically. And when we're thinking of it retrosynthetically, all right, well, how do we form that? Well, we know that we can form that from, and here I'm going to write it out, CH2, CH3, CH2, carbon, triple bond carbon, hydrogen. And if we do anti-Markovnikov hydration, which is hydroboration followed by oxidation, that gives us anti-Markovnikov, then we can get this. All right, and then this we can get from, so this we can get from our acetylide, and something, an alkyl halide like chloroethane. And then that we could get from just acetylene. And that's it. That's our retrosynthesis. Once we have a retrosynthesis, we want to turn it around and make sure that we know how to do this. So we'll start with and here we're going to put the reagents on the arrows. So we'll take sodium hydride, and we know sodium hydride will deprotonate that and give us that anion, plus what, H2 and what, some sodium ion floating around. All right, from this, we can then treat that with this halide, and we'll do an SN2, all right, SN2, and we will make CH3, CH2, carbon, triple bond carbon, hydrogen. And then in another step, we can treat this with water and sulfuric acid. Oops, we can't do that. We can't do that. That's going to give us Markovnikov addition. I caught myself. All right, so let's fix that. We can't do that. we're going to need to do the anti-Markovnikov addition of H2O, which is hydroboration followed by oxidation. So we'll get, in a first step, we'll use BH3 or some equivalent. An alkyl borane like 9-BBN might work really well for this. And then in a second step, we'll use the hydrogen peroxide and hydroxide ion, and then those will do the oxidation, and that will give us our aldehyde. So our product would be this aldehyde. All right, so that is an example of a retrosynthetic analysis. I picked a simple one here, and as you learn more reactions, you can do more complicated retrosyntheses. All right, we've got two more problems, number 37 and number 69. So here we've got one hexyne, and so here we're treating one hexyne with these different reagents. So I'm going to draw one hexyne up here. I'm actually going to draw it. Well, I'll draw it. So CH3, CH2, 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 C, triple bond, carbon, hydrogen, and there are 6 hydrogen or 6 carbons. 1, 2, 3, 4, 5, 6. Now I can tell this is a problem I have left over from a previous version of the textbook because it's one hexyne instead of hex one yne. All right, well, there you go. So now we are going to look at what this does, and I'm going to draw it as a skeletal type structure, just for, for giggles here. 1, 2, 3, 4, 5, 6, and then we'll put the triple bond like that. And that's not beautiful, but it's a triple bond. All right, so when we do these different reactions, we'll start with A, and I'll do A all the way up here. A is 2 equivalents of HCl, and 2 equivalents of HCl, we're going to do Markovnikov addition 2 times across the carbon-carbon triple bond. All right, this is sort of bugging me, so I'm going to see if I can fix this. There we go. That looks more like a, well, I don't know. Maybe that's not that great. All right, we're going to do Markovnikov addition 2 times across this carbon-carbon bond, and so that's a carbon as well. So 1, 2, 3, 4, 5, 6. And so Markovnikov addition, hydrogen will go to carbon 1, and the chlorine will go to carbon 2, and we'll do that twice. And so we will get 1, 2, 3, 4, 5, 6. Chlorine, chlorine. So HCl and twice, we get a geminal dihalide. In a similar fashion, if we use HBr, so B, 1, 2, 3, 4, 5, 6. Here we're going to get a geminal dibromide instead of a dichloride. All right, next we've got 2 equivalents of chlorine. With 2 equivalents of chlorine, all right, so we're going to add 4 total chlorines, so 2 here and 2 there. So we'll get 1, 2, 3, 4, 5, 6. So we'll get Cl, 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 and Cl. And so we'll get a 1, 1, 2, 2 tetrachlorohexane. All right, next we're going to do H2O, H2SO4, and HgSO4. We have to use the HgSO4, the mercury 2 sulfate, as a catalyst when we're doing terminal alkynes. So that's why we have that one. So for that one, that's going to do Markovnikov addition of HOH across. It will tautomerize, and we will end up getting a ketone. So 1, 2, 3, 4, 5, 6. And we will end up getting that ketone. All right, for E, we've got hydroboration followed by oxidation. And with the hydroboration followed by oxidation, that is going to give us let's see, that is going to give us anti-Markovnikov addition of HOH across the carbon-carbon double or triple bond. And so hydrogen will go here, and the OH will go here, and that will end up giving us an aldehyde. So 1, 2, 3, 4, 5, 6. And we'll throw the hydrogen on there to be perfectly clear that that's an aldehyde. All right, so that's E, F. With F, we're simply going to deprotonate with that sodium hydride. So I'm just going to write this one out. CH3, CH2, 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 carbon, triple bond carbon, lone pair, negative. And we would also get hydrogen and sodium, but this is the thing we care about, is that we're forming this, I'm not sure what you'd call this hexynolide, something like that. Anyway, so we'd get that. All right. On this one, the first step on both G and H is deprotonation. So I'm going to, so both G for step 1 and H for step 1 are going to form that same thing. But then we're going to have two different reactions. So G for step 2, when we react this, we are going to make a new carbon-carbon bond between this carbon and that carbon. So we'll have CH3, CH, oh, those are reagents there. So we'll have CH3, CH2, 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 carbon, triple bond carbon, CH2, CH3. And so we've made this new carbon-carbon bond, and so instead of having 6 carbons in our chain, we now have 8 carbons in that chain. And then for H, I didn't leave enough room here. Let's do it like this. So H, for step 2 on H, we'll take that. And here, this will open up that epoxide. So we got CH3, CH2, 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 carbon, triple bond carbon, CH2, CH2OH. And I'm going to put 2 and 3. 2 actually gets the alkoxide, and 3 gets us the alcohol. And so that would be that particular product. Oh my goodness. I was doing all that stuff off screen. I apologize. All right, I'll just explain this again real quick. So G, we end up getting 1, 2, 3, 4, 5, 6, and then 7, 8. And so we have 8 carbons there. So we took this that had 6 and added 2 more. And then on this one, we took the 6 carbons and we added 2 more and the oxygen, because we were taking this ethylene oxide and adding it there. Sorry, I got off screen. Sometimes I just get going. Okay. So in class, if I, that wouldn't happen, because in class, people would say, I can't see. All right. I love this. This is just marvelous. This is a marvelous mechanism. Mechanisms are fun. All right. That's something an organic chemist would say. But mechanisms are a fun thing to do. So when we're looking at this, we're saying, okay, we need to take this thing and turn it into this thing. And it's a good idea to figure out which carbons are which. And so let's label carbons that we're like pretty sure we know of. So for example, we're going to call this carbon 1, 2, 3, 4, and 5. So 1, 2, 3, 4, and 5. And then I'm going to call this one 6, 7, 8, 9, and 10. And those are all the carbons that are in our product. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8, 9, 10. So let's count those up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Well, now that we've analyzed which carbons are which, so we've got the carbon mapping, we want to figure out how it is that we're going to get to where we're going to start. And usually, if you can start somewhere, then you can use sort of your knowledge of other reactions to help you get to the next step. So the very first thing, we have to see what kind of compound this is. Well, this is formic acid. So I'm going to draw formic acid. Oh, I'm going to draw it in my dark pen here. So HO. So that's formic acid. And formic acid is, it's fairly acidic. In fact, here I'm going to draw the OH bond because we're gonna do full mechanism, so we want our arrows and everything. So we'll do a bond there and then hydrogen. So we're going to use that acid, and when you're looking at this, the very first thing you say is, I've got an acid. What do I do with an acid? Well, what does acid do? Acid protonates stuff. And if we go up here and look, what is most likely to be protonated? It's most likely going to be this alcohol. So we've got a lone pair of electrons on that, and let's draw that. So we're going to take this and we're going to protonate it. All right, so it still has one lone pair of electrons, but now it has a positive charge on it. There's that double bond there. All right, so 6, 7, 8, 9, 10. All right, so we still got everything. Well, now let's think, what is this likely to do? What kind of reaction are we likely to get here? Well, I mean, we could deprotonate it, but that's not really going to do us any good. So probably the most likely thing is that this is going to act as a leaving group, and we will get a carbocation that is here. And so I will draw that carbocation. So this is the point where you may want to like speed up the video because it takes a while to draw all this out. All right, so 6, 7, 8, 9, 10. So we still have all of our carbons and everything. Now, just in case you're curious, this also has a resonance structure. This is what's called an allylic cation. We'll talk about allylic cations a little bit later. We have a whole section on conjugated species. So it's an allylic cation, and if you just move that arrow, or you move that pair of electrons over, you'll get all right. And so again, 6, 7, 8, 9, 10. All right. We're going to use this particular structure in order to carry on our mechanism, but this is a resonance structure, which means that it was easier to form this cation to begin with when it has an additional resonance structure. That's why I point that out. All right. So now we get a carbocation. And carbocations they're electrophiles. They're going to seek out something with lots of electrons. And sure enough, we've got a nucleophile over here inside the same molecule, so it's easy to get to. So we're going to draw an arrow from that pair of electrons, one of the pi bond electrons, to that carbocation. So we'll do one of these over to here. And let's count real quick. We'll go back and look. So 6, 7, 8, 8 bonds to 1. This is 6, 7, 8. So this carbon is going to end up bonding to this carbon. All right, I'm making sure it's all staying on the screen here. So, all right. So so that pi bond still stays there. And here, and go back and look at what our product is. So there's carbons 6, 7, and 8, which means there's carbon 9 and 10. All right, we used one of the electrons in that pair. So we used one of those. Or one of the pairs of electrons there to make this new bond between these two carbons, between carbons 1 and 8. So that's carbons 1 and 8. And that means that we have a vinyl carbocation here. So there is a positively charged carbon there. All right, pause the video for a second and think about what is likely to happen next. And go back and look at our reagents up here and see what do you think is going to happen next. All right, hopefully you had a chance to think about it, and hopefully you said, well, we've got a carbocation there. Let's have a nucleophile react with that carbocation. So we're going to take the nucleophile that's here in the form of water. It's got that pair of electrons. It is just begging to go over here and react with that carbocation. All right, and so now, let's redraw this. All right, so let's see, 1, 2, 3, 4, 5, and then 6, 7, 8. And then carbon CH3OHH plus. All right, so now we've got that. We have formed a new bond between oxygen and carbon. And with that new bond between oxygen and carbon, we're really close to our product, right? We've got all the carbons there. We see where the oxygen comes from. Now, all we need to do is we need to deprotonate that. We'll deprotonate that. And when we deprotonate it, let's see here. And again, to deprotonate, I'm going to use water because it's an acidic solution. There's plenty of water to be found. All right, I'm glad I checked to make sure it was on the screen. We're going to deprotonate. It doesn't matter which one we take because we're going to take them both here in a minute. We also could have used, instead of water, we also could have used the conjugate base of this acid. It doesn't really matter which one. Something with a pair of electrons is going to deprotonate. And all right. All right, carbon 1, 2, 3, 4, 5, 6, 7, 8. We still have that carbon-carbon double bond. CH3O. H. And this is an enol. So this is an enol. Again, I'm going to use another water molecule. We're going to deprotonate draw the resonance structure, and then protonate. And then we're almost home on this one. So again, I'm going to use H2O because it is an acidic solution. We'll go to that hydrogen, take that pair of electrons, and it will go to oxygen. I got a little messy there. Sorry about that. All right, and carbon CH3O minus. All right, now that we've deprotonated that, you know, I shouldn't have deprotonated. All right, if it were a basic solution, I should deprotonate. All right, bear with me for a second. I'm going to pause. I'm going to fix this, and then I'll be right back. All right, sorry about the jump edit there. And so what we want to do now here is we want to look at acid. So we've got an acid here, HO, carbonyl hydrogen, and we're going to protonate that carbon-carbon double bond because it's an acidic solution. I was doing the basic mechanism. So we'll take this pair of electrons, we'll go to this hydrogen, and we'll go there. All right, and so now, now we're going to have a protonated species over here. And the, let's see, the carbon, the hydrogen is going to go here, so get rid of that. Have a single bond there. There's a new hydrogen that is bonded there. We have a positive charge there, hydrogen. All right, we can draw a resonance structure for this. We're going to take a pair, one of these pairs of electrons, and we'll draw a resonance structure that'll move that positive charge over. So do a resonance arrow. All right, we are almost home. We just need to deprotonate. Remember, when we're doing acid catalyzed enol to keto, we do protonate, resonance form, and then deprotonate. And so now we will do deprotonate. So we'll just take that OCH minus. All right, we'll use this to deprotonate. I probably should have used that earlier to deprotonate. And then that is going to give us our product. All right, and that is our product. If you compare, that's the same thing we have up here. So, all right, well, that is the end. That is the end of chapter 11. All right, so here I'm going to go over. There's our screen, and then that is the end. That's the last thing. So we are done with chapter 11. And for my Organic Chemistry 1 course, this is the end of the first semester of Organic Chemistry 1. and hope to see you in Organic Chemistry 2.